Hello everyone, welcome to Zero to LLMOps. I am Abhijit and we are learning Linux. So in the last session, we learned who you are on a Linux box, the users, groups, the account files behind them, and how you borrow authority. With SU and sudo, we ended with a service account, svc underscore fresher, owning our project directory. And if you ran bootloader.sh as that account, some of it probably through permission errors. That was on purpose. Today we fix it properly because today is the day we open up the permission system itself. Every file on this machine carries 9 little bits that decide who can read it, write it, and run it, plus 3 special bits most people never really understand, and a whole second layer called ACLs, access control list, for when 9 bits aren't enough. By the end of today, you can look at any ls-l line and read it like a sentence, and you can lock a directory down exactly the way you mean to. Let's give permission their teeth. So before we start, let's do a quick recall from before. Name the colon separated fields of slash etc passwd in order. The fields are username, then the X, the password which is stored in shadow, UID, GID, GECOS or comment field, home directory, and the login shell. Why did we give SVC underscore fresher has been no login instead of a real shell? So the answer is it's a service account, exists to own files and run a process. It must never be allowed an interactive human login. Third question, what is the trap with user mod hyphen capital G? And when you forget the hyphen small a. So the answer to that is bear hyphen capital G replaces all supplementary groups, wipes them. Drop yourself out of wheel. You lose the sudo. Always use hyphen small a capital G. Now, what is SU versus sudo? Whose password does each one ask for? So, SU hyphen equals the target user's password. You become them. Sudo, on the other hand, your own password. It borrows authority for one command. And which group grants sudo on rel and fedora by convention? So the wheel group via %wheel space all equal to in the bracket all space all in slash etc sudoers grants us sudo. The previous day was the foundation. Everything sits on top of today. Now let's move on. So here's what we are going to learn for the whole day. Every file and every directory has permissions for exactly 3 classes of people. The first one is owner, often written U for user. Second is the group, written G, and everyone else, written O for others. These are the 3 classes, and for each class, there are 3 bits. There is read bit, write bit, and the execute bit. We simply call them as RW and X. And for each class and 3 bits, RWX becomes the 9 bit in total. That is the whole left hand block you see when you run ls-l. Sometimes people gloss over and then get bitten by what RW and X actually mean in different for a file versus directory. On a file, it's the obvious thing. Read means you can read the contents of the file. Write means you can change them. Execute means you can run it as a program. But on a directory, execute X means can I enter this directory? Can I cd into it and read things through it? Read R means can I list what's inside? Can I run ls on it? And write on a directory means can I create and delete entries inside it. So directory you can R but not X is a weird half open thing. You can see the names but you can't actually reach any of the files. That distinction trips up everybody once in their careers. So we learn it now. Now let's learn the shorthand. Nobody says read, write, execute. For owner, group, and others, we use octal numbers. The trick is R is 4, W is 2 and X is 1. 4, 2, 1. Remember this. You add them up per class. So RWX is 4 plus 2 plus 1, 7. R and X is 4 plus 1, 5. R dash dash is just 4. So let's read what's the RWX, R hyphen X, R hyphen hyphen. And we get three numbers, one per class. So for RWX, for the user, it's 7, then 5 for the other, which is R and X, and then 4 for the others. So the number becomes 754. Owner can do everything. Group can read and enter, but not write. And other can only read. That one number, 754, carries all 9 bits. We will be covering these both directions in the lab until it's automatic. There are two ways to set them. By the octal method, we use chmod 750 and the file name. This sets all 9 bits at once. And there is another way, that is symbolic, where we use chmod u plus x or comma g minus w and then the file name. This nudges the individual bits. In our case, it is adding execute for the user and removing write from the group, and it's leaving everything else alone. You should always use the octal when you exactly know what permissions you want, and you can use symbolic when you want to flip one thing without touching the rest of the permission set. Chmod hyphen capital R walks a whole tree, and ownership is separate from permissions. Chown user colon group space the file name changes who owns it. chgrp space group space file name changes just the group. Let's move to the terminal and let's read some of them in the real modes. So ls minus l slash etc passwd and slash etc shadow. So here we can see that etc passwd gets for the owner, that is root, it gets read write. For the group it gets read, and for the others as well it gets read only permission. How this translates to the number? This translates to 644. Now on etc shadow you see that not even the root is having any permission, even though it is the owner. But as we said, the owner by default has the read permission, and root is a super user. So in root's case, it is different. It can read the files even though if it doesn't have any permissions. Now let's create a file, touch demo, and now let's see its permission. ls-l demo, we see by default it gets 644, that is read write, read read. Now let's do chmod 750 demo. Now the permission is read write execute, exactly the addition of 4 2 and 1, 5 read and execute for the group, and for others no permission, 0. Now let's try to flip one bit at a time. Chmod u plus u minus x, and then let's do g plus w demo ls-l demo. We see that we removed execute from the user and we added write to the group. So now let's talk about umask. So when you just ran touch demo, it came out to be 644. Read write for you, read only for group and others. You didn't ask for that. Where did it come from? A thing called the umask. The system has a maximum. It's willing to hand a brand new thing. So 666 for files and 777 for directories. Notice file never gets executed by default, and that's deliberate. A fresh text file has no business being runnable. The umask is a mask that gets subtracted from that maximum. The default umask on this box is 0 to 2. So take 666, which we get maximum for a file, and knock off the 022. You land on 644. Exactly what touch gave us. Take 777 for new directory, knock off the 022, you get 755. That's the whole mechanism. The umask isn't the permission, it's what gets taken away from the maximum. Umask with no argument just prints the current value. Umask 0 to 7 sets a stricter one for this shell session. Now the new files come out with 640 and the new directories get 750. So other gets nothing at all. That's a good habit on a shared box. But remember, that's only for this session. If you close the terminal, then it's gone. To make it stick for just you, add the umask line to your home slash dot bash rc. To make it stick system wide for everyone, it goes in etc profile or etc bash rc file. We'll set one live and watch the numbers change, and then let's put it back to the default value. Let's head over the terminal. So you mask VC 022. For now, let's not talk about this first bit. Let's look at only these three bits. By default, it is 022. Now let's change the umask value to 027. What it will do is now whenever we create a new file or directory, the default permission set that those will get is for file 650, and for directories it will be 750. So I have created a new file touch file1 ls-l file1. So we see have got read write, that is 6 read dash dash for the group, that is 4 and 0 for the others. Let's check with a directory as well. mkdir dir1 ls-l dir1. So we use ls-ld dir1 for the directory, and now we can see we have got 7 rwx for the owner, r and x for the group, 5 and dash, that is no permission, for others, that is 0. Now let's change that umask back to its default value, and let's now cross check it whether it is set or not. Now let's come to the special bits. The three bits almost nobody teaches properly. Beyond the nine we have covered already, there are three special bits that sit on top. Those are SUID, SGID, and the sticky bit. They exist to solve a real problem that the plain 9 bits cannot solve. Let's take the first one, and it's the most surprising, SUID, or we call it as set user ID. When it's on an executable, the program runs with the privileges of the file's owner, not the permission who launched it. Stop and think about it. How strange that is. Normally, when you run a command, it runs as you with your powers. SUID flips that. The program runs as whoever owns the file. The classic load-bearing example is passwd command. When a regular user changes their own password, that right has to land in the /etc shadow file, which remember from previous session is readable and writable by root alone. So how can you, a normal user, possibly update it? Because /usr bin passwd is owned by the root and has SUID bit set. So whenever you as a regular user run passwd command, for that moment it runs as a root user. It does the one write that it needs in the shadow file and exists. Without the SUID, ordinary users could never change their own password at all. How we can see it? We can spot it running ls-l whenever we would expect an X in the owner slot, we see S instead. So instead of RWX, we see RWS in the owner's slot. And how to set it? The octal value to set user ID is 4000. Add it in the front of regular mode. So chmod 4755 and the file name sets the user ID. Or symbolically, you could just use chmod u plus s on the file name. Now SUID is powerful and therefore dangerous. And SUID root program with a bug is a classic way that attackers escalate to root. So you set this bit rarely, deliberately, and only on code you trust completely. Let's look at passwd and prove the S is really there. So ls-l which passwd. So here we can see it has the SUID bit set. Second special bit SGID, or we can call it as set group ID. On an executable, it's the group version of what we just saw. The program runs with the file's group's privileges, but it is far more useful case. And the one we will actually use today is SGID on a directory. When a directory has the SGID bit set, every new file created inside it automatically inherits the directories group instead of the creator's primary group. Picture a shared team folder, five people from different primary groups all dropping files in, and without SGID, every file is owned by a different scattered group and nobody can read each other's work. Set the SGID on the directory once, and every file that lands there is stamped with the team's group automatically. That's exactly the problem we have with slash opt fresher project logs directory. Logs get written by svc fresher, but when we want to examine them, that folder should belong to DevOps trainee so the team can read them. SGID solves it. The octal notation of SGID is 2000. So same as SUID, we add it on the existing octal that we have, that we want to give permission as 2775, or to set just the bit, we can set it as G plus S on the directory. Remember, SGID can be set only on the directory. On a file, you set SUID. Now the third bit is called as sticky bit. On a directory, the sticky bit means only the owner of the file or root can delete or rename the file. Even if the directory itself is writable, anyone from the world, still the files inside it can be deleted or renamed by its own owner or the root. The textbook example that lives on every Linux machine is slash tmp. Everybody needs to be able to create files in slash tmp. So it's wide open for writing. But you absolutely do not want one user deleting another user's temporary files. The sticky bit is what stops that. You see it as T in the other execute slot. So the whole octal goes as DRWS, RWX, RWT, and the octal notation is 1000. You add it with your existing octal permission set so that 1777 and the directory name. Or just to flip the bit, what you can do is chmod plus T on the directory. Let's look at TMP and the trailing bit. So this is how we see the sticky bit is set, even in the var temp. ls-l ld slash tmp and ls-ld var tmp. You can look it yourselves. So this is the last piece of our theory, and it's the escape hatch for when 9 bits genuinely aren't enough. Think about the limit we have been living inside all this session. Standard permissions give you exactly one owner and exactly one group. So what happens when you need to say this one specific extra user gets read access to the file, but that user isn't the owner, and you don't want to add that user to the group because the group has 10 other people. You don't want touching it. So the plain RWX simply can't express that. That's what ACLs or access control lists are for. They let you attach permissions for additional named users and groups on top of the normal owner group other model. There are four commands by which we control the access control lists. Get FSEL and the file name shows us the full ACL picture, the normal permission plus any extras. Set FSEL hyphen small m space u and the colon username colon the permission rx space file. The hyphen m is for modify, grants the user read and execute without touching the owner group or other at all. Set FSEL minus x u colon username space file removes just that user's entry and set FSEL minus b file. This strips away every ACL for the file. Back to the plain permissions. So here's how you get to know a file has an ACL on it or not. ls-l shows a little plus at the end of the permission string. So our regular octal and the trailing plus. The plus sign is the system telling us there is more here than the 9 bits shown. Run getfsel to see the whole story. Miss that plus and you will swear a file's permissions are one thing while an ACL quietly says otherwise. One neighbor worth knowing while we are here, chattr. It sets file system level attributes that are separate from permission entries. The big one is chattr plus I. Plus I means immutable. A file marked immutable cannot be modified, renamed, or deleted, not even by the root user, until you clear the flag with chattr minus I. It's how you protect a critical config from an RM or a runaway script. lsattr shows you which attributes are set. Let's grant an ACL, watch the plus appear, then read it back. Let's go to the terminal. Touch ACL file test. We have created a file for our demo. We'll modify its permission by chmod 640 ACL file test. What this is telling is this is readable and writable by our user student. It's only readable by the group student and others do not have any permission on that file. Let's look at get FSEL. Here's the detailed view. The file name, owner is student, group is student, user has read write permission, group has read only permission, and the other doesn't have any permission. Now let's modify using setfacl hyphen m our user fresher01 and let's give read permission to that user. And let's look at now ACL file test. So this plus sign tells us that we have some certain access control list permission for that user. To know what all permissions and which user, we simply run get FSEL ACL file test. So here whatever our regular permissions were that is written plus the user fresher01 has a read permission is what we get to see. So that was the theory. 9 bits, umask, thus 3 special bits, and ACL. Now 2 hours, you yourself should do a hands-on of whatever I am going to run for now. Let's start with the octal drill. Touch test file 01, ls-l test file 01, chmod 640 test file 01, ls-l test file 01. So we created a file with a default permission set and then we set 640 that is read write for user, read only for group and others don't get any permission. Now let's add an execute permission chmod for the user. So chmod u plus x and for others let's add a read permission. So here we can see the user has got rwx and the others have got read only permission. Now let's make a test directory mkdir test dir, and then let's give it a permission chmod 700 test dir. So we should create this directory somewhere where all the users have access to. So let's create this test directory in temp folder cd/tmp. Let's see if we already have such directory. No. So mkdir test dir, and let's see its default permission using ls-ld test dir. So even student can enter the test dir, and if you go to su-fresher01, we can go into test dir. Now what we do is, let's come back to the student user and chmod 700 test dir. So what it does is, it locks down the permission so that only the owner has the permission read, write, and execute, and no other user gets the permission to do it. Let's log into the fresher01 user, and let's now attempt to go into the test dir. So we get a permission denied error. Even we cannot list anything from the test dir. Now let's go to the part 2 of the lab. Let's be our own student user. Let's look at umask value. The default one is 022. Let's set it to umask 027. Our umask is set. We checked it using the umask command. Now let's touch F1 ls-ld, sorry, not ld, just L, because it's a file. So here we see that by default it gets read, write, read, and none for the others. Same way we can do mkdir d1 ls-ld d1, and we see by default we get 750. Here we got 640. Let's set the umask back to its original. Now for part 3, the exact commands for SUID, SGID, and sticky bits. Let's look at ls-l/usr bin passwd. There is the S in the owner's X slot. ls-l/tmp. Notice the T in the others execute slot. Now let's prove the group inheritance. So let's sudo mkdir-p/srv shared, sudo chgrp devops-trainee/srv/shared. So we changed the group ownership of this shared folder. Sudo chmod 2775/srv shared. Now let's act as fresher01 user. Sudo -u fresher01 using the sudo command touch/srv shared from _fresher. Now let's do ls-l on/srv shared from fresher. Here we see the group permission that it got is for DevOps training group. Now let's look at sticky directory. In this we will prove only owner can delete. So sudo mkdir-p/srv sticky test. To set the sticky bit, sudo chmod 1777/srv sticky test. Now let's create a file using fresher01 user. Sudo -u fresher01 touch/srv sticky test owned _by _fresher, and touch/srv sticky test owned _by me. Now let's look at the files inside /srv sticky test. So these are the two files and their respective owners and groups. Now let's try to delete the owned by me file, that is the student ownership file, using the fresher01. Sudo -u fresher01 rm/srv sticky test owned by me. Cannot remove this file, operation not permitted. Now let's move forward to ACL. So let's create ACL test file, get facl, ACL test file, set facl. So before setting the facl, and this file cannot actually live here. It should be in shared folder. So let's move it ACL test file to SRV shared sticky test. So let's go in SRV sticky test. So here it is our test file. Now let's go to the fresher01 user sudo -u fresher01 ls-l ACL test file. Okay, so let's chmod 600 ACL test file, and now let's try to. Okay, so sticky bit has got affected here. We can't use uh, sticky test folder. Okay, so we went ahead in the OPT, and here we have put our ACL test file because it's a common location. And that's the reason we have put the ACL test file here as the home directory. We would have needed the permission to home directory. That's the reason we are putting it here. Now here we can see the ownership of ACL test file is with student, and the others, that is fresher01, shouldn't be able to look at the file. But look here, we have a plus sign. That means it has ACL set on it. To get the information, we do get FACL ACL test file. So here we see, apart from our student's own permissions, the user fresher01 has a read permission. So let's try to prove it. Sudo -u fresher01 cat ACL test file. So this user is able to do the operation for ACL test file. As a student user, we are also able to do the operation. Now to remove any FACLs, we simply do set FACL -b ACL test file, or for a specific user, you can do -x and the permission name. And now let's try to cat ACL test file. From student, we are able to do it. But from the, as a fresher01 user, we get permission denied error. And let's look at ACL test file. The plus sign has gone away. The part 5, the final bit, and this is for all incremental project, so that we should lock it down properly. So we are now going to change the ownership, and that too with the recursive format chown capital R SVC fresher DevOps trainee /opt fresher project. So we are giving the group and the user for this fresher project. Now let's change the ownership to 750. That is read write execute to the owner. SVC fresher 5 is read and execute for the group, and others don't get any permission. 750 chmod 750 opt freshers project. But for the logs, we want to set the SGID bit so that the new logs inherit DevOps trainee group. So sudo chmod 2750/opt fresher project logs. Now, as we know that we are not in the DevOps trainee group, that we can confirm with the ID command, but we do need to manage, or we do need to execute files from OPT fresher project. So for us, let's set access control list using setfacl. I keep forgetting to sudo setfacl -m u colon dollar user for our own user rw not rw r and x read and execute permission /opt fresher project. Now let's do a get FSCL on the /opt fresher project. So student user has a R and X command permission. So to check this, sudo -u svc underscore fresher our service account /opt fresher project bootloader.sh. So we ran our script. Again, we do the same. And now let's look at the new logs using ls-l. The new logs that came in have the DevOps trainee as their group. The T4 evolution of the script, we will add a umask 0 to 7 line at the very top of the script, right under the shebang bin bash. So every log file it writes is created with 640 with that lockdown permission. No access for others instead of the worldwide reachable 644 it was getting before. This is the day's umask lesson applied to our own project. Let's open the file and let's insert the umask. Umask 027. So in the script we have added the line. The rest of the script is not changed. So today we added that line plus the SGID on logs from part 5 means every future boot log lands as SVC fresher colon DevOps trainee mode 640 readable by the team close to everyone else. Do not change anything else in the script today. So let's do the recap. We learned about 9 permission bits read, write, execute for owner group and others. And on a directory, those mean list, create or delete and enter. Octal is r equal to 4, w equal to 2, and x equal to 1, and it is summed per class. So rwx r hyphen x r hyphen hyphen is 754. The umask is what gets subtracted from 666 for files and 777 for directories. Default 022 gives you 644 and 755. Three special bits. SUID runs a program as its owner. That's how passwd writes shadow. SGID on a directory makes new file inherit the directories group. That's how our logs stay DevOps trainee. And the sticky bit means only the owner can delete like slash tmp. And ACLs are the escape hatch. When one owner and one group aren't enough, watch for the plus in ls-l and you can read it with getfsel. The homework is OPT Fresher project should now be 750 owned by SVC Fresher DevOps trainee with an SGID on logs folder and your ACL on it and bootloader.sh should run clean as svc underscore fresher and drop a 640 log. Three questions before we close. Convert rwx r hyphen x hyphen 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 to an octal and 640 back to symbolic. What does SGID do on a directory and why did we put it on logs, and what does chttr plus I protect against that plain permission can't. In the next session, let's go over the text processing. First will be grep and the regex fundamentals, anchors, character classes, quantifiers that everything from sed to log hunting is built on.